Hello, hi. Can you hear me, Larry? Let me see. Your microphone looks to me mute.
There we go.
Okay, yeah, good. You can
It
see me,
was.
right?
Yes, I can. Thank you. Nice to meet you.
Okay, how are you?
I'm good, thank you.
Okay. Um,
Sorry, the lighting in my room is not very good.
I just put a extra light because this
Yeah,
light is also pretty bad.
yeah,
But your background looks fantastic, actually. Let me just,
yeah.
yeah, just close the door. Just one second. Okay, dokie.
Yeah. So
So,
in Zoom, you can set a background picture,
okay,
right?
I
So
didn't.
yeah, it's just a little thing like to make your background look less boring.
Okay. So, what's the plan for today? Um,
Well, I guess this is more like a meet and greet to find out what
mhm.
your intentions are and what the plan might be if we do a podcast or some sort of
Yeah,
continuing kind of thing. So
yeah,
if
sure.
you can give me some ideas of where you're coming from and
Mhm. Yeah, it will be a podcast for general audience, obviously, uh, because when I took some of the science classes, like when I was small in high school or school, none of the stuff that I'm reading today was ever mentioned.
yep,
And if I when I studied those, some of the stuff didn't make any sense. Some of the stuff are too complicated,
yep,
and there's a like formidable barrier of technicality unless you go to some technical like PhD or graduate study.
that doesn't always help.
Exactly. And plus, some of the area are highly like guarded by the barrier of technicalities
Mhm.
because most of the stuff is not for the general audience.
Yeah,
And but if somebody can see that whatever they're reading in the book is not the end of the story, there's a other
yes.
side of the story that is still open to explore, not because it's discredited, just I would say, but because it was not explored in that direction.
Yes, it was not, it can be explained differently. And
Mhm,
that's where I'm coming from. My favorite, very favorite Richard Feynman
mhm,
quote that I put in all my papers actually
mhm.
is there's always another way to say the same thing
Mhm.
that doesn't sound at all like the way it was said before. Okay,
Exactly.
so Richard Feynman said this at his Nobel laureate speech. Okay,
Mhm, mhm.
so that when I read that, I went ding, 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 ding. That's right. It's not that all the work I'm doing isn't contradicting necessarily the
Exactly.
mainstream.
Mhm.
I'm just saying it differently.
Exactly.
And it's helping people. The way I'm saying it in my videos,
Yeah, definitely. Good.
I
Good
get
luck.
emails all the time from people
Mhm,
saying they had a breakthrough today.
mhm.
Somebody emailed me and said they had a breakthrough because, and yeah,
And you can explain it.
not every day, but I'm exaggerating, but very often people email me and say, your ideas really made me think,
Mhm,
right? It really
mhm,
gave me a lot to think about. And then through the thought experiments, which I love,
mhm,
they get their breakthrough. So it's happened a lot. And I'm really, quite pleased with how this
mhm,
is going.
mhm.
So I
Yeah.
understand. I understand exactly where you're coming from.
Okay. Now, regarding the content that we want to discuss, because I think I emailed you a broad content. So from those, we can stick with uh, the the core contents first,
Yeah.
and as the time goes by, whenever some relevant contents comes,
Mhm.
we can explore depending on the
Yeah.
time slot or depending on how
Yeah.
relevant the concept to the current discussion.
Right.
But we can focus on some core concepts.
Yeah.
And I would also like to explore a little bit the historical development of ideas so that we don't want to jump to the latest model or cutting edge. rather
Yeah.
than we can talk a little bit how
Mm.
it was initially proposed and
Yeah.
why
I'm
it
not,
got
you know,
rejected.
okay.
Mhm, mhm,
Okay, so just to be really super clear,
mhm,
I'm a move forward kind of person,
mhm,
and I've already done the look back. Like I've
mhm,
already done the look back,
mhm.
and
Yeah, those
I,
those ideas you
I
already
don't want to
explored.
spend too much time looking back,
Yeah, that's right.
right? Because
If you already
maybe
have a
if
content, if
right,
you
I would
already have a
rather
content,
say
exactly.
I'd rather say something like they did this experiment, they
Mhm,
interpreted this way.
mhm.
Maybe it'd be better if we interpreted this way, but
Plus,
not
if you
dwell too
already
much on
have
that.
a, sorry, if you
Yeah,
already have a video that you explain the stuff, you can always send us the link
yeah,
of that existing video so that we don't have to
sure.
duplicate the
Yeah,
same
okay.
thing again.
Yeah, for sure. Yeah,
Mhm,
yeah. I just, wanted to be clear that I don't dwell on the past too much. And so I
mhm,
know like it's important to stand on the shoulders of greats, and I've
mhm,
already done
mhm,
that.
mhm,
Right. So, I don't want to have to burden, like, if there's another way of saying it,
mhm.
of saying how things work and how the universe works, we should just start saying it now.
Yeah.
Almost like we need to start from scratch.
Okay. Okay.
Right.
Yeah, I agree.
So, yeah. Yeah. And, I'm working with other people on this as well. Other people have, like I say, had their breakthroughs,
Mhm,
and they realize that most of the problem is with the language in theoretical physics. Like you say, it's too complicated. It's too, would you say, there's a barrier of technicality.
mhm,
I like that. I wrote that down because there is a barrier of technicality, and you can get buried in the technicality and
mhm,
not really, like, can't see the forest for the trees.
mhm.
So what you
Exactly.
need to do is show, what I'm trying to do with my video series is find that root thing,
Mhm,
the fractal thing
mhm.
that can be scaled from one scale to the next scale to the next scale, and then just try and teach them that one thing.
Okay.
That's what I'm
Mhm,
trying to do,
mhm, mhm.
right? It's all, I'm
So,
trying to do from
so
scratch.
tell me a little bit about you. For example, so far the videos I saw,
Yeah.
I could not find like your background, how you got interested into that particular subject, and also what you do in the as a day job. So
Oh yeah.
I
Okay.
guess you're
So
engineer, so you can
yeah,
elaborate
well,
on
okay. So I will give you the quick synopsis. It's a
that.
long story, but I'm a computer scientist, so I have a degree in computer science.
Hmm.
And then I worked, so I don't have a PhD, as I told you.
Hmm.
I have a bachelor degree. And I realized early on that academia would not be for me, but I didn't want to leave the university. I
Hmm.
loved the university. And so I worked, after I graduated, I worked in astronomy for 10 years.
10
And so
years
for
as,
10
as a
years,
job or just a
as a
separate?
job,
Okay.
I started as a summer student in after second year.
Hmm.
And then when I graduated, I continued to work for them for, so from second year to when I stopped was 10 years.
Hmm.
And then, so I did instrumentation for them.
Hmm.
So this was, building mechanical devices that hook up the telescopes that are used for, you know, studying stars. And the
Hmm.
one main project I worked on had to do with polarimetry, which looking at magnetic fields of stars, which is
Hmm.
interesting because now I'm really interested in magnetic fields. But
Hmm.
back then I didn't know, like, I'm a computer scientist, not a physicist, but I always found myself sort of surrounded by, astronomers and physicists. So I was always interested in that. That's why I picked the astronomy department. I picked them. I said, I want to work for you. And they hired me. So then I wanted to work in the medical field. So I
Hmm.
went to, there's a research institute called Robarts Research Institute, which is at Western University in
Hmm.
London, Ontario, Canada, right? That's where I live.
Hmm.
And I went to them and I said, I want to work for you. Because I knew, like, astronomy was winding down because they were merging with physics, and I knew they were phasing out a lot of jobs. And so I didn't feel safe. And so I knew I had to do something. So, I started working in the field of medical imaging. Now,
Hmm.
medical imaging, and astronomy are kind of very similar because they're both about imaging, right? And
Hmm.
I'm also a little bit of an artist. I have an
Hmm.
artist bent in me. So I always look for, like within medical physics, I am doing visualization. Like I like to do visual things. So I like to, build user
Mhm.
interfaces that are super easy to use. And, these are, we build instruments that actually go into the operating room and they do
Mhm.
surgical procedures. And so these are complicated devices, right? And
So in
so,
terms of imaging, what's your specialty? Like real-time X-rays versus MRI versus, or what kind of
yeah, yeah,
imaging?
all of it. MRI, ultrasound, 3D ultrasound, okay, is my area of expertise. So
Mhm.
it started with us building at Robarts. We actually were one of the original inventors of 3D ultrasound. So this was back
Mhm.
in 1993. So we developed our own 3D ultrasound technique,
Mhm.
and then we started a startup company, and then we licensed our technology to a bunch of ultrasound companies. Excuse me, and then I went back to Robarts because I wanted to do more research. And then, so I've been at Robarts since 1993,
Okay, so you have
right?
a
That's
long expertise.
quite a long time with them, a lot of
because
experience with
because
MRI,
mhm. If you
ultrasound.
study for 5 years without actual doing the experiment or troubleshooting the equipments or
That's right. Well,
troubleshooting the experiment, because people
yeah.
do graduate study without
Oh,
actually doing real high
yeah.
quality experiments.
Yeah, no,
So,
I did all my stuff is always hands-on. Like Ian, okay, so I'm really proud of this. When I worked in astronomy, of course, I was a computer scientist, but I didn't know anything about electronics, but I was very interested in it. So they taught me everything I know about electronics. And I
mhm,
had to build my own devices because astronomy was poor. They didn't have any money. So I couldn't,
mhm,
like, even back in this was in the 80s. So in like the mid to late 1980s, it was very expensive to get a circuit board made. So
mhm,
I had to hand wire wrap my circuit boards myself and then troubleshoot them with an oscilloscope and make them work. And then, so back then they just invented those little single chip microprocessors.
mhm,
And
mhm,
so I rebuilt their whole, like they had this polarimeter controller device. That was a big thing. And then I said,
mhm,
I can do everything on this one chip. And so
mhm,
we rebuilt everything for this one chip. And then the astronomer used that
mhm,
to study magnetic fields of stars.
mhm.
So
So, but we don't hear much about magnetic fields of the stars, because most
oh
of
yeah,
the time what I hear is the gravitational field or
yeah,
some.
no, I mean there are magnetic fields around stars, and
Yeah,
they
yeah,
have
but we don't we
effects,
don't
and
we don't hear
they're
about the news
they're
or the
measurable.
science or update, because
Yeah,
most of the updates,
yeah,
they heavily focus on gravitational field rather than
yes,
magnetic part. It's in the
right,
background.
and that's a big mistake. That's a
Mhm,
big mistake, I believe. Okay, so here's one interesting, and not to do with stars necessarily, but more to do with black holes.
mhm, mhm.
Okay, so I went to a workshop, yeah, at the Perimeter Institute. I don't know if you know who they
Yeah,
are.
I heard. Yeah,
The
it's a
Perimeter Institute of Theoretical Physics.
prestigious
They're
one.
in Waterloo, Ontario.
Mhm,
Okay, and so I kind of weaseled my way into a workshop there on black holes. And it was Neil Turok,
mhm,
right? He was the director of the Institute at the time, and a bunch of other astronomers and
mhm,
physicists and astronomers, but mostly like cosmologists, right? And so one guy, I can't remember his name, one professor gave a talk. I really wish I could remember his name off the top. I'm not good with names, by the way. Um, so he gave a talk and he did some simulations,
mhm,
and his simulations showed that the jets that you see around black holes
mhm.
can be created from magnetic fields alone.
Okay.
Magnetic fields alone can be the cause of those giant jets, right?
So
And so
they are always there. So.
that was the first time I heard of that.
Mhm.
Right? So
Yeah.
magnetic fields are okay, super important, the most important thing, more important than gravity.
Mhm,
And gravity and magnetism are basically the same thing. Okay, we try to say they're two things. We try to say they're different things, but they're the cause of gravitational attraction is the same as the cause of magnetic attraction, in my opinion.
mhm. Okay.
Okay.
That part actually, the science textbooks actually they treat magnetism and the gravity totally independent. They
Yeah,
have nothing to do with with
yeah,
each other, as far I
yeah,
understand.
Yeah.
Because
Um,
initially gravity was just
yeah.
mysterious force, then it became the curvature of space-time, but curvature of
Mhm.
space-time doesn't go well with the quantum system,
Yeah,
so
exactly.
electromagnetism is
So,
quantum, so they're trying to separate this thing totally
yeah.
separate.
And right. And that is a kind of a big mistake, I think, because what they should be trying to do with gravity and quantum mechanics are just different, completely different languages. And
Mhm.
so it's the languages, I believe, that can't be reconciled, not the phenomenon itself, right? So just through my research, and I don't know if you know anything about Ken Wheeler, because I talk about him quite a bit in my
I saw
videos.
a couple of videos, yeah.
Yeah. So he, what he says and what I agree with is that, it's, you know, especially regarding attraction, forget about repulsion from that,
Mhm.
right? Because nature favors attraction. Nature favors attraction, right? I'll
It
show you.
favors attraction because
Because if, excuse me, if I take two gravitational bodies and put them near each other, they're going to attract each other, right?
that's the
Yeah,
general
okay.
idea.
That's,
Yeah.
you know, if I take two magnets and hang them on strings, I
Mhm.
had an experiment, but I took it apart, so I can't show you right now. But and
That's
plus,
yes.
my screen looks weird. But if you take two magnets and hang them on strings and bring them close to each other, they're going to always attract,
Mhm.
right? They're always going to come together. One's going to, if they're in repulsion, one's going to turn
Mhm.
and it's going to attract.
We'll
So
find a
nature,
sweet spot to attract
it's
eventually.
going to turn. Like I can do it with, you know, see it with my own eyes that when I bring two magnets together in repulsion, one of them always turns quickly and then attracts. It wants to attract. It conspires to attract. So, you know, so in that sense, gravity and magnetism aren't that different. The shape of the field of magnetic field is different than the shape of the field of a gravitational
Mhm.
field,
Mhm.
right? Because of the coherency, because of the polarization of the magnet. So
Mhm.
that's the difference. That's the difference. You've got gravitational field and you've got, which is like a circle,
Mhm.
and then you have the magnetic field, which is like, you know, think of two balloons that are, you know, going in opposite directions,
Mhm.
right? It's polarized, polarization. And so that's the only difference between gravity and magnetism is coherent, okay, like a laser. It's exactly like a laser, exactly like a laser. It is, you know, when you make a magnet coherent, what you're doing is taking all the interatomic atoms inside the magnet and aligning them.
Mhm.
Not all of them, but a lot of them.
How do they actually make magnet so that the it's more aligned, it's more like in a like laser. For example,
Yeah.
matter like
Mhm.
disorganized and
Yeah.
they have
Yeah. Yeah.
the
Yeah. Yeah.
force all over top.
So
But
yeah.
how they align everything together so together they exert force on the external material. So
So
do
okay.
you know how to
So
make
I
magnet?
know how they make a magnet, right? You know how
Hmm.
they make a magnet. You take a hunk of metal
Hmm.
and you wrap a coil around it,
Hmm.
right? And then you hook the two ends of the coil up to a battery,
Hmm.
right? Maybe a car battery.
Hmm.
Actually, a friend of mine's doing a video on this right now, so I know exactly. He's doing this experiment. So if you coil a coil around a piece of
Hmm.
metal, iron, of course, you want it to be a ferrite metal,
Hmm.
and then hook that up to a battery, the current is going to go through and it's going to coil around
Hmm.
the material, and that is going to cause all the domains to align.
But that's the temporary magnet. The moment you
No, no, no,
remove the,
no, 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 no,
it will
no.
become permanent.
If it's an iron
Hmm.
material, if it's a something with a high permeability, they call it,
Hmm.
then it, you know, it'll turn into a permanent magnet on the spot, right there. You know, you can do a temporary magnet with a weak battery, like a 9-volt battery. You can't make a
Hmm.
permanent. You need like a 120 volts. You need like a bunch of. You need a lot
Hmm.
of a huge potential to make an actual permanent magnet. But you can do it. You could
Oh.
do it, right? You
So
could do
as
it.
if my commonsensical understanding is by passing through strong electrical force, you're inducing a magnetic force that makes the material of the iron molecule
Yeah.
becomes more aligned because they are
Yes.
also magnetically responsive.
Correct.
something like that. Okay, okay.
They're
And
magnetic responsive. They're like, it's called high permeability, but that just means that they can easily be aligned. Now, the language that I'm using, the language that I want to change to, because the mainstream denied the ether, right? But I want to bring back the ether because I believe what's happening, and a friend of mine is doing experiments on this right now, is that this, when you coil the wire around a piece of metal and then you pass current through it, what you're doing is you're spinning up the ether. You're spinning up the ether like a gyroscope. So when you have a gyroscope and you sit it on the table, it's got no poles. It's just a hunk of metal. It's got no, you could put it any direction. You spin it up, now it's got one direction. Now it's got poles, it's got an axis. Once you spin it, it's got poles, it's got an axis. So every little, right? So every little atom is like this. But when you spin, you know, the bulk of the ether, all the other gyroscopes line up with that, and that creates, and that becomes a permanent condition because it's more efficient for, you know, for it, basically. It's conservation of angular momentum. It's actually more efficient. Once you align them all, it wants to stay like that until you heat it up, and then it doesn't like that.
Yeah, because that again, when you heat it up, by definition, molecule becomes more like disorganized, and they want
So
to
there's that, the
move
Curie,
away from the material because of that.
so there's a certain temperature where all the magnetism will just, the Curie, what's it called? Curie temperature.
Yeah, regarding the ether, actually, there's a lot of controversy, right? Because in general, my understanding is based on Michelson-Morley's experiment, they got rid of ether.
Okay.
But my commonsensical few observation, couple of things. I'm not a engineer or not even a physicist, so correct me whatever I say or put your comment. If there is no media, then how come they communicate?
Okay, so there is a medium. Okay, there is a medium, and that's the answer. So Michelson-Morley did not disprove the ether. Okay. They had an ether model, in my opinion. Everything I say is in my opinion.
Yeah, exactly.
From my research, from what I've studied. Okay, so the Michelson-Morley, they had an ether model. They had an ether model that was wrong. They had an ether model that, you know, that we are, you know, the planet Earth is going through a static ether. That was their model. The Earth is going through a static ether. They were actually trying to prove the ether with their model. They weren't trying to disprove it. They had a model and they said, if, you know, if our model is right, then we expect these results. But they didn't get.
That means they are expecting a velocity of Earth against the ether, but they found null result or something.
Right. So they disproved their model of the ether.
Okay.
Right. They didn't disprove the ether. You can't disprove anything, anyways, but they disproved an incorrect model of the ether, in my opinion. Right. So there can be a medium. I believe there is a medium for the propagation. I call it the medium, or the medium for the propagation of light. I call it the ether because I like the word. And it's
because the medium, everybody says about electromagnetic wave, because by definition, wave needs a medium. But somehow the quantum mechanics or something, they got rid of the medium.
Yeah, quantum mechanics is, in my opinion, again, kind of a hack. It's just much simpler with a medium. So why get rid of something and then make it more difficult?
Yeah,
if you got rid of something that made it more difficult, and nature, it is not difficult. Nature is very simple. So working in the field of ultrasound actually gave me a lot of insights into this, right? Because ultrasound needs a medium.
Exactly.
Right? I know that ultrasound needs a medium, and I know that the speed of sound of, you know, tissue is, you know, 1536 meters per second, and I know the speed of sound of water is 1486 meters per second, or whatever it is, right? So you know, so I know that to propagate ultrasound you need a medium. To propagate any wave you need a medium. in
Mhm.
my opinion. So I think it's just simpler. Like instead of saying, "Oh, we disproved the ether," which they didn't. They disproved a model of the ether that they had that
Okay.
that was
Okay.
wrong. And so that's I think that there could still be an ether, and in my opinion, it makes life so much easier because then you can use the same math that
Mhm.
you use, and they do use the same math. What they do is they rearrange things. They create a barrier of technicality. I like that term that you use
Mhm.
because
Mhm.
they
Mhm.
created a barrier of technicality with they call things different things, and they call the same thing different things, and they call different things the same thing, and they really their language is really
Yeah.
messed up. It's like
Unless you're in the club, you'll not understand the language, what they're
I don't
referring to.
know.
Probably it's referring something very simple.
I don't think they understand it because I've had conversations with these people, and I've gone,
Mhm.
are they, do they really understand what they're talking about? Or are they just saying the right words, to, I don't know. It's kind of, because I've met Neil Turok. I've met him a
Mhm.
bunch of times, and I tried to get through to him in some of my ideas, right? But they are so locked in to their language. It has to be their way, or
Definitely.
their way or the highway, right? They don't want to hear any other way. And I don't understand them. I understand they were trained that way.
Mhm.
And, if I was trained to, oh, here's a good example. When I was younger, I was trained to write in a certain language. It was called C.
Mhm.
And then they came along and said, oh, now we have C++, and now we have object oriented. I had to continuously change
Mhm.
my language to do my job. But it wasn't fun. Nobody wants to do that.
Mhm.
Nobody wants to change their language. And so I want to rewrite the language. That's what I'm trying to do. I want to rewrite the language that the average person can understand, right? And I think I'm getting close to doing it, and I'm helping other people do it too.
Is there any name you gave to your language?
With what?
Is,
Do I have a
did you
name?
give any name to your language?
Well,
It's a work in progress.
I'm calling it the principle of incommensurability, actually.
Okay.
And I
Okay.
don't know if you saw any of my videos on that, but and I got a lot of these ideas from Crazy Ken Wheeler.
Mhm.
But so it's the principle of incommensurability is kind of like the foundation class. Like in computer science, you always have a base class. You always have
Mhm.
something, a foundation that everything else is built on. Right. And so I have this thing called the principle of incommensurability, and it can be applied to any field of study.
Mhm.
So the idea is that it's kind of simple. It's kind of, think of the yin yang.
Mhm.
Think of the yin yang. You've got the black and the white, and you've got the black, big part has a white circle inside, and the white big part has the
Mhm.
black circle inside. Okay. And so the principle of incommensurability states that nature works by two principles, right? Two principles, and these principles are incommensurate. So incommensurate means no basis with which to compare. So I use the example, I say, oh, in the beginning was darkness and God said, let there be light. That's just something I say, just, because people are familiar with that.
Mhm.
So darkness and light are incommensurate because darkness is not light and light is not darkness, but, the universe is everything in between.
Mhm.
So it's not the light or the darkness that really is important. It's the conjugate nature. So these two principles come together to
Mhm.
create phenomenon. So that's where I get.
I thought by incommensurable you meant, or in general, it meant that you cannot measure because it's not
Yes, that's
measurable.
a wrong. That's a kind of a, a not quite right interpretation
Mhm.
of that word. If you go back to the root of the word, it's more like orthogonal. It's
Mhm.
more like real numbers and imaginary numbers. Like real is not imaginary, imaginary is not real, but you can put them together and create a complex number. So
Mhm.
you can't like add a real number to an imaginary number and get a real number,
Mhm.
right? Or you can't add a real number imaginary and get an imaginary number, right? But
Mhm.
you can put real numbers and imaginary numbers together and get complex numbers.
Mhm.
And so that's the conjugate nature, but real and imaginary I would call incommensurate, because can't measure real numbers against imaginary numbers. So you're right about the measure part, and you can't measure imaginary numbers against real numbers. So that's where the measure comes in, the measure idea comes in. There is no basis with which to measure one against the other.
Yeah, I was just
That's
trying
the
to
exact,
understand the word's meaning itself, because the word meant is not like commensurable means able to
yeah,
pinpoint, to
yeah,
measure it down. So
yeah,
incommensurate means you cannot, although suppose an example, I think the famous magnet example. So in right in a just one second. I think in a rod magnet like this,
yeah,
there should be a middle point that
yeah,
will be the edge of the North Pole, and
yeah,
there will be an edge of South Pole. So I can, in my mind, I can think that the North Pole started right there, and the South Pole started right there. If I cut it, make it a smaller piece. But at the end, it's not pinpointable, because if I cut through exactly in the middle,
yeah,
all my concept will break down. There will be no edge. So even though on the surface I can see, I can measure it in the middle, but if you actually want to measure it, it's not measurable. So I was
yeah.
thinking in that direction,
Well,
that
that's,
do you
that's,
something like that?
yeah. Yeah, so the way and that might be a perfectly fine way of using that word. I don't,
Okay,
that's
okay.
not the way.
Because I just looked at the word's meaning itself. So
Yeah,
you can explain.
exactly. And I do that too. I do that too. So the one definition I liked is no basis with which to compare. So in my mind, when I hear that, I think, well, in order to compare something, you need two things,
Mhm.
right? You need two things. So in order to
Obviously.
compare anything, you need two things.
Mhm.
So in my mind, I read that as you've got two things, two concepts, and there's no basis with which to compare one with the other. There's no basis with which to, like, I can't make an imaginary ruler and bring it up to a real measuring stick and measure anything. Like, that's it. I think my interpretation is more
That they're
holistic,
in the orthogonal. That means they're independent. They're
orthogonal. Yeah,
dissecting or
so real
crossing
and
each other.
imaginary or orthogonal, dielectric and magnetic or orthogonal, right? So in the magnet, there's two concepts that are orthogonal to each other. There's the magnetic and the dielectric. The magnetic field is exactly orthogonal to, so the traditional magnetic field, which are the flux lines, okay,
Mhm.
are exactly orthogonal to the isopotential gradient, which I'm trying to bring to the public, because this is the isopotential field around a magnet is actually the thing that makes the magnet work. This is the field that they don't tell you about. So if you do a search for a magnetic field, you're always going to get the flux lines. You're always going to get a picture of the flux lines. You're never going to get a picture of the isopotential lines, which is a pressure gradient. And so then you realize, oh, magnets work by the principle of pressure mediation.
So
There's
for
a
this
pressure
magnet,
gradient. Yeah,
the there are two lines you mentioned. One is the flux line.
yeah.
The flux line will be like this, right? But if you look from this direction, will
Yeah.
it be the other magnetic field you're referring to?
Can I share my screen with you?
Sure, sure.
And
Yeah,
show you
that would be great.
Okay, so I will do that and I will share this screen. Okay, so you're still there. Okay, so this is the picture I'm talking about. Okay, this is the pressure gradient.
Mhm.
Okay, so here you've got, that would be the North Pole and this would be the South Pole. And if I, right,
This is a ball magnet, round, right?
it's a spherical magnet.
Okay.
Yeah, so I generated this. A friend of mine, his name is Mike Snyder. I have it up
Mhm.
here. He wrote the software, excuse me.
Mhm.
He wrote the software to generate these lines. Okay.
Okay.
And so, and they're not really lines, they're actually surfaces. They're actually surfaces. So they're not really lines. So the flux lines of traditional magnetism, those are lines because those are vectors, those are pointers, those are like
Mhm.
pointers, they're lines. So those are lines. But the equipotentials, so basically,
At
if
any point, they will feel the equal, like force.
No, any point on this line is going to feel equal pressure.
Okay.
This is a pressure gradient. So, and pressure is force, but pressure is force. Oh, I actually have a slide on that. So I really like unit analysis. So the units of pressure are the Newton per meter squared. So Newton per meter squared means like we're talking about a surface, because meters squared are the units of the surface, right? And so, you know, we're talking about a pressure gradient, which is not that much different than the pressure gradient of a weather system. Okay, so now we can combine so in a weather system, you've got, when the lines are close together, you've got a large pressure gradient. And in a large pressure gradient, you have strong winds. And then over here, you see like lines that are far apart is a small pressure gradient, that's weak winds, you know, small winds. So here, I've got a similar thing where here I've got a really high pressure gradient around the magnet. And of course, you're going to have strong winds, or you can say a strong force. You're going to feel a strong force. And over here, the lines are further apart, and that's a small pressure gradient. So, you know, if I place a small magnet out here, it's going to feel less force than if I place a small magnet in here. If I place it here, it's going to go wham right to the magnet. If I place it here, it's going to go right to the magnet, but you know, it's not going to feel the force as much out here as in here. So this is the real magnetic field. This is the field they don't show you though. So they confuse you with like flux lines or nothing. Flux lines are just the orthogonal of this pressure gradient. All these little, I don't know if you can see these little red lines here in the background, right? That's where iron filings would line up. If you placed iron filings, you know, iron filings line up along the flux lines. Oops.
Okay.
So you know what I mean? So they show you this one, which is where the iron filings line up, but this is the guy that does all the work. Because you know what? If I place a magnet right here, right? If I place a magnet right here, if I measure the potential right in the middle, let me go back to my, so this is the dielectric, this is the inertial plane, this is the block wall. If I take a Hall sensor and measure the voltage, or, you know, measure the pressure right here, it's going to be 0. It's 0 pressure right here. This is like 0 pressure, null pressure, low pressure.
Just to clarify, can you see my mouse cursor? Can you see my?
I know I can't actually. You know.
Okay, so so where's the North Pole and South Pole in this figure? Top and the bottom, right?
This could be, yes, this could be, if this is north and this is south, yeah.
Okay, okay.
Right,
So
and this
in
is
the equator, roughly, in common sensing term, the line you're referring to roughly in the middle.
Is the equator, yeah. They call it the block wall. Ken Wheeler calls it the inertial plane. It's really, but it's the point of 0 pressure, low pressure, which is why there's a huge force this way and this way. Why the magnet is stuck together. If you put another magnet here, that null pressure zone is going to move to in between the 2 magnets. So if you take 2 magnets and put them together, right, then the null pressure zone is going to move from here. All these pressures you're going to get this picture where you're going to have a magnet here and a magnet here, North Pole here, South Pole here. Those 2 magnets are going to become 1 magnet. Exactly 1 magnet. So, yeah, so that's, you know, so the traditional magnetic field is the incommensurate, orthogonal to, or incommensurate of this field.
Okay, so there another one thing I want to just ask in this particular picture. So my understanding is there is a magnetic field and the electrical field associated with the magnet. Is that right?
If this is the magnetic field, okay, so the term electric field actually is a little bit confused historically. So I'm a little bit hesitant to answer that question because I'm not really sure. When you say electric field, are you talking about electricity?
Yeah.
About electricity?
That you can measure the voltage.
Yeah.
Just by presence of a magnet.
Right. So with a permanent magnet sitting still, there's no electric field. Right. So with a permanent magnet sitting on a table, there's no electric field.
It has to move.
It's a
To
magnetic.
generate a electrical field.
Yeah, and that's a different, that's a whole other story. You
Okay.
have to,
Okay.
you have to
But
know.
I was just thinking that in
Yeah.
this picture you mentioned two orthogonal.
Yeah. So, okay, so good question. That's a good question. So some people call this orthogonal field the dielectric field. That's why I didn't want to get confused, because back in the day, like Steinmetz and Heaviside and those guys, they called it the dielectric field. And the dielectric field is more radial. It's more radial coming out. And so these little dots here would be the dielectric field. And I believe this should be the magnetic field, these round ones, because they go in a circuit. Right? So yeah, and so the historical magnetic field, you have, the flux lines going from the south to the north, and they come out and they go this way.
Okay.
Right?
Okay.
So, and then this one is going more like, but see, this is a flow field, I believe. So the orthogonal one is a flow field. And so this is ether flow. So these little guys here could represent ether flow. And then ether flow creates
what flow?
Ether flow.
Ether flow. Okay. Okay.
Like wind, ether wind. I was talking earlier about the weather patterns. So I'm kind of pretending that ether is a kind of a wind or a flow of some sort, right? So the flow, what happens, the flow creates a pressure gradient. Whatever, like however the flow is happening, and I'm trying to figure this out with my friend, because he's doing the actual electric, he's making magnets from scratch and trying to figure out, what's going on in reality when you create a magnet, right? And so, we don't have all the answers, obviously, but I think this field is much more informative. Because, okay, so when I take a magnet and I put it right here, it flies up here.
Yeah, exactly.
Because the pressure, it doesn't want to sit here. It wants to go here, or it wants to go here. If it's a little bit below the dielectric plane, then it wants to go here. If it's a little above, and it wants to go here. But guess what? What happens when I put a magnet here? What happens when I put a magnet here? What direction is it going to go?
It will stay there in the same direction towards the surface, right?
It's going to go like that?
Yeah.
No.
Is that right?
It goes like this. If I put a small magnet, a tiny like ball magnet, I'll show you. I think I have that in here. Okay, I have a little video. Hey, I'm glad I had this handy. Okay. You watch. See, it wants to go along this line. I'm kind of pushing it, so that's a little bit cheating, but let's have a look at this one here. So this, if I touch it, it goes that way. If I touch this one, I just touched it a little bit, and it wants to go that way. And this one wants to go that way.
But if you push directly towards the ball, what will happen? You push towards the side.
Yeah, I know. Let's see if this is the one.
Okay, exactly the video I was asking for. Okay.
Yeah. Okay, I think this is the one. Let's see.
So after,
I'm proving that I can keep it on the line, right? It's not wiggling all over the place. And then, yeah, I'm pretty sure this is the one. I'm trying to induce it, but it's too far away. And then, oh, that's not the one. There's one where I push it and it goes. This was actually meant for a video. Oh, there we go. Here we go. Watch. So I place it there, and I push it a little forward. And instead, see, it went forward, and then it went on the isopotential line. So it started to go, right? It started to go forward, and then it stopped, and then it went this way, because this is equal potential line, right? This is the line of the of least resistance. So when you play, see, you can see my diagram here. When I place it like a little spherical magnet there, they all turn, right? I can't turn it the other way. As soon as I place it on the table, it turns right away to point this way, but it sits there. And then if I just touch it a little bit, it starts to go, and it wants to go this way. Like an object in motion remains in motion, Newton's law, right? And if there's not much friction on the table, there's, you know, gravity's pushing down, there's some friction, so it's not perfect. But if I place it here and tap it a little bit, it starts to go this way. I never knew that before.
Yeah, my common sense was your earlier 2 video where it goes directly to the surface.
Yeah, when it's right in the middle. So when it's right close, when it's like right on the edge, like there's going to be a sweet spot. So right here, I calibrated it so that this is the spot where all the forces balance. And if I push it even a tiny bit more this way, then it's going to go to the magnet. So that's what this experiment was just showing that. I'm just going to touch a little. I'm trying to find the spot. Oh, I'm not actually playing it right, but all I did was touch it a little bit, and it went flying to the magnet. So there's a spot in there. There's friction on the paper and everything, but there's a spot where if I just touch it, it's going to go to the magnet.
Okay.
Right, but when I'm back here, when I'm back a little further, you see that it goes the other way. So there's a kind of, I call it the strong force and the electromagnetic force. These are exactly, here's the other thing that's really interesting. These lines are exactly electron orbitals. They're exactly electron orbitals. I might even be able to show you that. And it's quite shocking, actually. Let's see if I have that.
Like in the most of the atoms, the ordinary electron, like first, second, third, fourth, etc., etc.
Yeah, like the, you know, the
orbitals, yeah.
The orbitals, yeah.
Okay.
I'm just trying to find the exact rate. This is the same one. Yeah, I don't have the orbitals in this one, but you know what I mean, right? Yeah, that's the same one. I had a slide. Yes.
The magnetic isopotentials lines, they are almost like a route for the
here we go.
for the planets.
Right. Yeah, exactly. Yep. So here are the orbitals. The top are the electron orbitals. These are the, the probability distributions. And here are the predictions by Michael's software if we place the magnets where, so plus would be north and, minus is south.
In the screen, I haven't seen anything. It's still blank.
You can't see my screen? Oh, I have to share this one. Okay, I have an idea.
No, I was seeing, yeah, right.
You see that now?
Yes.
Okay, so the Zoom software, the software that you're using, it only lets you share one application at a time.
Okay.
So if I switch to another one, you won't see it, which is good, I guess. But so this is what I'm talking about. Let's look at the 2P one, because the 2P one is the same as it's this, right? So this is the same software, right? And we just kind of simplified it a little bit. So there's what Michael's software generated, and there's the orbitals, the probability distribution. So this is exactly. So here are the orbitals, the 3D orbitals, and here's what his software predicts. And then you've got the 4F orbitals, right? And there's what his software predicts. So what I basically am starting to say is that a magnet is an atom. It's an atom. So a magnet that's just got one north pole and one south pole, it is it is a hydrogen atom,
Mhm.
basically, at a large scale. So on the fractal paradigm, we've scaled up the phenomenon that happens around the atom. We scaled it up to
Mhm.
the human scale.
Mhm.
And so this,
In the hydrogen atom, there is, in conventional sense, there is a proton and electron. So, so you're saying in
I'm referring to the field rather than the particles.
okay.
Okay, when an electron is bound to an atom,
Mhm.
then this is the pattern that you get of orbitals. This is
Okay.
the pattern that you get, and it's the same as what they model, right? So
Yeah,
what
they're looking very
is this a
similar.
proton?
Very
Is this an
similar.
electron? Like this is the same as what they model. So they're, so this model is, it's been around for a long time. This is what,
Mhm. Yeah, that's the standard model, I believe, right?
standard model, yeah. So this is creating the same diagram, which means that the phenomenon, the pressure gradients, the
Mhm.
physical model, it should be the same.
Okay. Yeah, that's
So
interesting. So
so
if
this is when I'm doing my experiments with this,
mhm.
with the the little magnet. That's a little sphere magnet, but it does the same thing with the ball bearing,
Mhm.
right? So it magnetizes it and then it goes along these isopotentials. I discovered that by accident because I was trying to do the experiment to see how far can I get the magnet before it stops attracting. And then I got up here and I gave it a push like I showed you, and it went sideways. I'm like, whoa, why did it do that? And then
Mhm.
I leveled, so I have my level here. So I leveled everything. I thought, oh, it must be gravity doing that. But no, it still does it even when everything's leveled. And so, that got me to thinking that, I'm literally playing with an atom because I'm mapping out. I can actually, I can see literally the
The orbitals.
orbitals, right?
So these experiments are reproducible. That means anybody can check, right?
Yeah, sure. Because all you have to do is buy a magnet. These
Mhm.
are like $20 on Amazon, and you can get these at anywhere, K&J Magnetics. So
Mhm.
that's what's so shocking. Like everyone, when they think about magnetism, they're
Mhm.
always thinking two big magnets coming together, two big magnets of the same size coming together.
Mhm.
Nobody's ever thinking of big magnet and small magnet, except
Mhm.
for guess who? The MRI guys,
Okay.
right? Because in the MRI machine, you have a big magnet,
Mhm.
which is the MRI machine, and you have a small magnet, which is the hydrogen atom. So the only reason the hydrogen atom works in the MRI machine is because it's a tiny magnet.
Mhm.
They even call it a magnet. Like the MRI people know that the hydrogen atom is a magnet. And what happens is the hydrogen atom aligns itself in the magnetic field.
Mhm.
So in a magnetic field, this would be hydrogen atom lining up along it. See, it lines up along the isopotential lines.
Mhm.
That's what I discovered. So when you place a magnet there, it turns so that the halfway point
Mhm.
is always lined up along the isopotential line. But that can only happen if the big magnet is really big and the small magnet is really small.
Okay.
If you have
Okay.
a big magnet, then you've got all these you've got all these pressures mediating, and you don't get that effect. But when you put a small magnet there, and you can see that these potentials not even touching the next potential line, like the pressure are mediating here very nicely. And it's the lowest pressure when this is pointing to the magnet, right? And so then it just wants to sit there because
So,
it's
so
too far away to be attracted to the magnet,
mhm.
but it's still not too far away to be affected by the magnet because this thing turns to point to that over
Mhm.
here. It just doesn't go flying to it,
So
right?
in your experiment, or in general, in your opinion,
Yeah.
how rapid the orientation becomes in presence of the magnet? For example, if you turn the magnet on in the center, the big magnet you're talking about,
Yeah.
how fast the the tiny magnet would reorient themselves towards the bigger one. So what's the
Super
speed?
fast.
You think
Super
it's
fast.
the speed of
I've
light
seen,
or something?
I played around with that, so it wants to do it so fast. So
Mhm,
I'll put it down, and it's just going to be boop in
mhm.
like a millisecond. It's going to turn.
Okay.
It wants to turn. You can't not make it turn. It's impossible.
Okay.
So yeah, I've got a lot of little magnets. I've got some long cylinder ones, and they always want to turn. Like they always want to turn, and they always want to line up, so that their equatorial plane is lined up along an isopotential line.
Mhm.
Right, and so mainstream says, oh, they align their domains to, so the flux line goes this way. So mainstream says they align to the flux lines, and I say they align to this line, and neither of us are wrong. Neither of us are wrong, right? It lines up to the flux lines, and it lines up to the isopotential line. Depends on the perspective. It's like clockwise or counterclockwise. It's a matter of your perspective.
Yeah, if you compare the plane of inertia, the inertial plane you just mentioned,
Yeah,
if you think the inertial plane orients towards the isopotential line,
yeah,
but the poles aligned along the flux line, something
yeah,
like that.
exactly. So I don't know which one is causing.
Mhm.
See, is it the flux lines causing them to line up along the isopotential lines, or is it the isopotential lines causing them to line up along the flux line?
Yeah,
So
because
that's
one thing I can add, because you just mentioned even though the tiny magnet is not feeling the attraction yet,
yeah,
but they are still orienting. That means the
yeah,
flux line is not the dominating force, especially in the far away,
yeah,
rather than the isopotential line.
yeah. It's possible that these dominate out here,
Yeah, exactly.
and that at a breaking point, then these dominate, and that's what it looks
Flux.
like. So here's what happens. And I have this little diagram's really good, because what happens is, if I push a magnet this way, so
Mhm,
it's going to go follow this line.
mhm,
It's all on its own. It's going to roll. Even if I put a little gravity in, I let it roll, it'll roll along. It'll go backwards. I have
mhm,
another video. It's not in this PowerPoint though, where I place a magnet here, and then it goes backwards and goes all along this line. And then it gets to a certain point, and then it flies to the magnet. So when it's doing this, it looks like it's doing isopotential, but when it gets to here, it looks like it's following the flux line. So I think you're right. There's kind of like a breaking point where it can't mediate the pressures anymore. And now it's easier
too
for it to go
close.
this way.
The isopotential lines are too close at some point,
Yeah,
then some margin of error is very low. So with
yeah,
some minor friction bumps, they're off and they started to get attracted directly,
yeah.
like
So what's
along the
happening
flux.
is, with pressure mediation, what's happening is you get cancellation, pressure cancellation.
Mhm,
So then it's creating a low pressure system is all the way along to the magnet. So it's, so each of these has its own fractally scaled isopotential pressures,
mhm,
right? Each one of these is a little pressure. And guess what? This isopotential line, when I measure it with a Hall sensor,
mhm,
reads 1 point, let's say 0.01 volts.
mhm,
And then this is 0.02 volts, then 0.03 volts, then 0.04 volts, and so on. So you can see it's getting faster and faster and faster.
mhm,
Here, it's 0.01 volts, 0.02 volts, 0.03 volts. You see what I mean? This is
mhm,
scaled down, but it's still, um, it's just a scaled down version of this. And
mhm,
this is a fractal
mhm.
version of the big magnet. Right down to even the pressures,
Yeah.
right? So that's, these are I made a lot of interesting sort of discoveries by looking at these.
Mhm,
First of all, looking at a small magnet against a big magnet, and
mhm,
then accidentally discovering that these guys weren't going right to the magnet, they're going somewhere else. And
mhm.
so this is not, I don't remember ever being taught that.
Did,
I don't
did you
ever remember
did you
being
do
shown that.
a did you do a similar experiment where instead of two magnets, you did one big magnet in the middle, in the top, and a tiny, just a metallic rather than like they are not themselves magnets yet.
Oh yeah, no, ball bearing. This can be a ball bearing too.
So they behave similarly. It doesn't have to be a separate magnet, right?
No, it doesn't. No, in fact, my original discovery was with the ball bearing and not with the magnet. I started with the ball bearing and then I said, oh, I wonder if the magnet does it too. And with the magnet, I could tell, like, because I can measure the poles.
Mm-hmm.
With the ball bearing, I couldn't tell
Which
how
one
it
is which? Yeah, exactly.
how it was orienting itself along the isopotential line, but with the magnets, I could tell. So I've got some cylinder ones, and the spherical one's hard to tell, but when I put two together, it was clear because one would go here and one would go here, and then, you know, they would line up along here.
Okay.
So yeah, so that got me, you know, this
Mm-hmm.
geometry here.
Yeah, that's pretty interesting because I did not expect it, because when you asked me where the magnet will go, my answer was it will go straight to the ball. But actually, it's like
That's what
going
I thought. That's what everyone thinks, and you
that's totally non-intuitive, right?
know, my boss is a medical physicist, and I'm
Mhm.
sure that's what he thinks too. I haven't shown him any of this stuff yet. I don't know if he's watched my videos or not, but
Mhm.
you know, he's fairly old, and so old, and I'm old too, but he's older than me.
I'm
And
also, everybody's
old people are very hard to change their minds, and so he's a medical physicist. He was taught physics a certain way.
Mhm.
They teach it a certain way. They, you know, it's really hard to break their mindset and show them, you know,
Yes,
a different way.
sometimes I think even though their or our or somebody else's interpretation
Yeah,
or way of thinking is totally different,
yeah,
because at the end, whatever they're getting the result or experiment the result, because they can work with the result,
yeah.
they don't care if you have a different way of explaining, because they say, okay, I already understood this way and it is working, so why change it, something like that.
Explanations don't help them. They
Yeah,
don't need explanations. They just need, here's an
yeah,
experiment, here's the
exactly,
results. We say
exactly.
this, so we must be right, and
Hmm.
that is wrong,
Hmm.
right? You might not, you can still have the wrong interpretation and get the math right,
Yeah, exactly.
right? So yeah, that's and I've made
that,
found a lot
that, that, that one thing I can say, the limitation of professional expertise, because they are already getting the result, no matter how you interpret and which method you use,
of,
as
yeah,
long as they are getting the right result, they don't care about the interpretation.
yeah.
But
But
as an
we have,
amateur,
yeah,
amateur like you and me, I am more interested in the interpretation
yeah.
rather than if the result works or not. If the result works, but the interpretation makes me satisfied and is like self-consistent or intuitive,
And that was
go for
exactly what
that rather
I,
than
yeah.
uh, non-understandable, but at the end you get a result, and that result is doable or reproducible or uh, something you can work around.
Exactly. I just what I you said the word satisfied. I wasn't satisfied. Like I tried for years and years and years trying to do it their way, and
Mhm.
I just wasn't satisfied. I just wasn't satisfied. And I had no skin in the game because I didn't have a PhD. I didn't have anything to have to defend, you know what I mean? And but I was still working with professionals, and so I knew how it was done. I know how it's
Mhm.
done. And so then I was just like, okay, I'm just going to do it my way. I'm not going to do it their way. I'm going to start over. I'm going to take, you know, take no prisoners and just see where it goes, right?
Yeah,
And, you know, it's really come a long way.
yeah. This is another one thing I just wanted to mention. We don't want to discuss it today, but sometimes later. Just keeping in mind, there is a like big emerging field of transcranial magnetic stimulation as a
What?
independent fellowship.
Say that again?
Is in the medical field.
Yeah,
There are a lot of fellowships, like a specialization,
yeah.
and that is board certified or something. So there is a new emerging field is called transcranial magnetic stimulation to treat a
Transcranial.
lot
Yeah,
of different conditions.
yeah.
So that means somehow by because all they're doing, they're putting because they're not putting any magnet inside the brain yet. They're doing
Electrodes.
everything from the surface.
Yeah,
So by reorienting and manipulating the two poles, that's the,
yeah.
I guess that's the most important thing they can do. They
Mhm.
can change your perception of pain, your perception of anger, anxiety. or even some motor impairment. Sometimes people are weak in some facial muscle or something.
Yeah, yeah.
So exactly.
Yeah.
So these magnetic manipulation and
Mm,
the fields
yeah.
has, in addition to MRI and some other imaging that we already proven the concept of effect of magnet on the body, they're taking to the next level as a therapy.
Yeah,
So
yeah.
it would be
I can see
interesting
that.
because
I can
this
see that.
magnetic alignment happens instantly, and
I've always like when I was younger, I always thought magnets would have some sort of healing power. I
Mhm,
did an experiment that you might find interesting
mhm,
with alfalfa seeds. So I took alfalfa seeds and I took some of them and I exposed them to the south pole of a magnet, and I
mhm,
took the rest of them and exposed them to the north pole of a magnet. And I expose them sort of on the edge of the magnet because the edge has
mhm.
a stronger, stronger feel, stronger attraction. And then I germinated them and did raise them or whatever. And the South Pole, and I did this twice because the first time I wasn't sure, so the second time I did it, and the South Pole seeds germinated better, they grew better, they looked better than the North Pole seeds.
Wow. So
So
that means even in a magnet,
yeah,
although quantitatively, like North Pole and South Pole are interchangeable in terms of their strength,
yeah,
qualitatively they are different.
something is different. Something is different.
Because
I
you just said that on South Pole,
Yep.
seeds germinates better.
Yeah, yeah, yeah. So yeah,
So
yep,
something obviously
yeah.
different here.
And that's where these two, that's where the okay, we can get back to the incommensurability then,
Mm-hmm,
because I'm calling this the magnetic field, and
mm-hmm,
I'm calling the other one the dielectric field, and I believe it's the dielectric field that has the asymmetry. The magnetic field seems to be perfectly symmetrical. I can't measure a difference. In fact, I can't measure a difference between north and south. I can't measure a difference between N52 magnet and M50, 42 magnet of the exact same size. So the magnetic field is very symmetrical. But because of the principle of incommensurability, in my mind, I'm thinking, okay, well, the other principle, the incommensurate principle, if one is symmetric, the other has to be asymmetric. Because the principle of incommensurability means whatever one thing is, the other thing is not,
okay.
right? So something is asymmetric, and I believe it's the dielectric field or the dielectric component of the field, because it's all really just one field. And so the dielectric is the inertial plane, right?
Mm-hmm.
The dielectric is like more the inside of the magnet and not the outside of the magnet. So whatever's going on inside of the magnet is asymmetrical. So, I don't know. It's interesting. I just don't know enough about that to say there is definitely a difference with those seeds. And Ken Wheeler says that he can measure the difference with the ferrocell. Do you know about the ferrocell?
Yeah, actually, I just ordered one ferrule cell. It's a glass, right?
Yeah.
$70. I
Did you
just
get it
put the
from
order.
Tim? Did you
So
get
I
it?
don't have it yet, but I will have it soon.
Did you get it from Tim Vanderelli?
Actually, I just went to the website
Oh
ferrocell.usa.
yeah, yeah, that's Tim. Sorry.
Yeah,
Yeah, ferrocell.
straight
Yeah.
from because
So
I looked most of the time I ordered this kind of stuff from eBay. eBay didn't have a single product.
no,
So
no,
I
no.
had to
His
go to
his are the
their official website. I
his
think
are the
I
his are the best ferrocell.
patented it, right? They patented it. Like
Yeah, I have one. He actually lent me one of his really good ferrocells, and
Mhm,
he gave me one of his supercells last year. So
mhm, mhm,
and I tried making my own. I had some good success actually making my own. I made my own light box, right?
mhm, mhm. Yeah, I just put the order of the slide. I did not put the entire
Yeah,
lightning because I
yeah,
just wanted to see how far I can go. And if I think, oh, it's really doable and I can do some good experiments, so
yeah,
then um, for
yeah,
the taking of the picture, I think you need the entire thing to take
yeah.
quality pictures.
Exactly. Yeah, yeah. So it's a little tricky. Using the ferrocell is a little tricky, right?
Hmm. I
Um,
never used it, so I will have some
can
question once I have it.
actually help you. Like, you can just use one light. You don't have to have a circle of lights. I did an experiment with continuous lighting.
Hmm.
So, you can try different light sources and see what
Hmm.
happens.
Yeah.
Polarizing or whatever. Yeah. So Tim's done everything. Done all of it.
I think at this point we can conclude today, right? Roughly, and we'll continue next week, something like that. So
Okay.
once in a week is okay with you,
Yeah. Like,
roughly?
are you recording these sessions, or what are you trying
I
to do?
think it recorded automatically. So I think whatever we talk is recorded. I can give it to you.
Okay. Cool. Well, I didn't know that. I would have been.
No, actually I did not put the recording button, but I can see it's the Zoom has a default.
Oh, I see. Okay. Well,
Yeah,
good. That you don't have to
it's
think about it.
recorded automatically in my account. So next time, I don't know. I can always edit out the first and
Oh,
last.
no, it's fine. No, I don't mind. Like, whatever. It's fine. That's actually makes it a lot easier if you don't have to think about whether you're recording.
Exactly. So by default, we assume that it's already recorded because that's the default. I did not hit the
But you
button
know
yet.
what? This was a great conversation. Thank you.
Yeah, I
I
think like if you give me a little bit of heads up, these are the things you'll discuss. I can write down simple questions as
Mhm.
an audience,
Yeah.
and you
No.
can answer
Mhm.
or clarify. That will like be
Yeah.
because today I was totally like open.
Yeah. No.
I
I
didn't
mean,
know what you will be
it
talking.
worked out really good though, and I had my slides kind of handy, so
Yeah.
because I was working on them earlier today, so you were lucky you got to see a lot of stuff that'll be in my next video. So
Let me don't cut the line. Let me stop the recording. Then I'll talk for a couple of minutes.
all right.
Just one second. Let me